regulations and law enforcement there. But you're right. There is technology that exists today that should be able to communicate with a handheld phone.
And it might even help in a building. It doesn't have to just be a car. The person who's in a building.
Well, let's just set the example. I'm familiar with National Institute of Science and Technology. Did a case study. They had a building that was about to be torn down, and the question is, if the firefighters are in there,
right.
Let's say it's a burning building, how do they communicate, and what is the obstructions for that continuing? So it's not hearing related, but it is life threatening.
Right.
And
it's situation awareness.
Yes, and it turns out, as you might imagine, you have spots where no communications, and the other spots that you do, but you would like to have more. So the point being is, if this building is burning, and let's say we have smoke detectors that go to ADT or a service, why not have at least some that will withstand a fire?
Right.
And that's not difficult.
Right.
So that's a positive. But the net result was that they came up with a certain range of frequencies that seemed to be able to penetrate most of the building structure. Mm-hmm. And this isn't calculation. This is actually field experience. The whole building was instrumented quite. It was a building down in the Washington area, if I recall, Washington D.C. In fact, I know the person that was in charge of that. Well, I know them, but they both retired from this, unfortunately. So they aren't immediately available. So, again, my point would be, this seems almost perfect for a gathering of people of interest, having a very structured agenda, and the usual breakouts like most of these have. But I would come in with the questions posed: how would you handle this? And here's what we think is the upcoming situations that need attention. And you would get to decide for the user community, in the case we're talking about here, the hearing impaired, and those that are essentially into the transmitter business, in other words, radiation of electromagnetic fields. And that's the big picture. That's called compatibility.
Right.
And that's what I've been doing for more than 2 years. How about 50?
Right. So it's compatibility, and for me also interoperability. So like if a manufacturer wants to make a product, then these products should be interoperable in this setting of this compatibility.
But there's interesting people that think about we think about interference with electronics.
Yes.
Well, we talked about human exposure earlier on this chat with you, and people said, "Well, that's not an electronic." It says, but it's a receptor of this energy.
Right.
So why are we cutting it off between electronics and a human that's acting like an antenna?
Right. Because my implant is acting as an antenna. I have it implanted.
Exactly.
Yeah. And because I'm a different body weight than somebody else who has this device, I may have a different response to it because I have less. Yeah.
The way in which the leads are put in is quite. In fact, it's a very complex subject because you're looking at the penetration and reception of a field in a dielectric solution, which is your body fluid.
Right.
And that's even difficult to calibrate.
And now I'm sitting in my car with Bluetooth around me, sitting on a seat that has electric heating in it and holding a steering wheel that's heated. And I am thinking about this, what's going on in my car.
Yeah, probably 60 hertz stuff isn't going to bother you at that point, other than maybe a hum in the voice band.
Strangely enough, I've had a lot of interference, electronic interference, and when I had
but it's probably what that is feeding. The radio system, the one the light that comes
on. So I've been shocked by my defibrillator 16 times over things like that. 18, 800 volts directly to the heart is not a fun experience.
That's why I went to University of Oklahoma. Be very careful in that experiment.
Exactly.
To know what you can do and how far away the source has to be.
Right.
Has to be.
Right. And a lot of people don't appreciate that because they're optimizing for solving the problem quickly instead of solving the problem correctly.
We spent 3 or 4 years on the project at Oklahoma, and we have published papers on it. But essentially, we solved the problem as far as we couldn't do any more experimentation.
Right.
Okay. Now that's a good many years ago now, and I'm just wondering if that's ended up in a storage facility in a library.
I think people look at things like battery life. They come up with different answers because people tend to think battery life is a linear function, and it's not. And depending on the kind of battery and the charging,
it's the power
it's a
supply
complex,
the battery is feeding.
Exactly, and so there's a transformer there. There's all kinds of aging issues, chemistry,
well, there's the other thing
stuff
too
like
is
this.
that some of these have rechargeable batteries, and they're usually putting it down like even your Apple iPad, and it's wireless charge. There's no connection. But if you look at
The inductive coupling.
if you look at the electric vehicle, they have a loop underneath the car and a loop embedded in the ground, and they charge the car, but it's 20 kilowatts of energy, not this milliwatt from your phone. And the question there is, it's not even enclosed in a chamber because the sides of the cars are right.
It has to be open. Yes, it has to be open because the
fact,
car is not closed. And so I will not drive an electric vehicle because I don't want.
Certainly don't charge it with going over the loop. Charge it
with the plug.
With the plug.
Right. But I mean, you could make a mistake. You could drive somewhere and suddenly someone else has got your car and they park it for you in a valet spot, and then you have to go pick it up and
have someone else pick it up.
Right. But this is the kind of thing that a typical person might not know, and it's difficult to be vigilant in these situations.
And we got to be careful we don't over-exaggerate, because you lose our credibility
Exactly.
if we do that.
I mean, as you pointed out before, a lot of people just want to look at this thing and find a problem instead of actually being aware where the problems are.
Yeah, well, and to the good extent that this level of RF for human exposure was as I said, 1/50th of any effect. Yet when you do a compliance measurement, so to speak, if you're within 1/10 of a dB of this number that's 1/50th, oh my God, the words.
Well, dBs are so imprecise anyway. So people are, and Gauss. I mean, try to measure Gauss, right? You got a Gauss meter.
Well, measurement uncertainty is a favorite subject of mine. I'm certain of that.
Excellent. One day we have to talk about that because, these Bucky fields the inverse Bucky fields for MRI machines, it'd be very interesting to have a discussion
Well, even
about
just
that.
a simple measurement with an antenna of that FM radio station, if you look at the instrumentation chain and the uncertainty of the components of the chain to measure that, it's about a 6 dB uncertainty. Well, that's a factor of 2 to 1. So if you're looking at, you go up to your boss and say, well, I can get the measurement within 6 dB. Well, that's 2 to 1. Can't you get closer than that?
Probably not.
The answer is no.
Right. I mean, what are you using to measure it? And, what is the Nyquist frequency of that measurement? And, there's a lot of variables there that you have to account for. And besides that, once it's broken, it's broken. So it's always outside. Like, for example, this device that's in my chest. I'm going to turn this off.